Okay, welcome everyone to the CARS workshop, and this CARS, by the way, has nothing to do with the Formula One race that was going on a couple of days ago, or the last couple of days. But it is actually one of the longest running workshops at RecSys. I believe Moshe can correct me if I'm wrong, but maybe the first edition was 2009 or 2010. So it's been going on for a very long time, for a good reason, right?
Sorry, please keep going.
Because context is, of course, very important, right? People say context is everything, right? That's also true in recommender system. It's 1 second in here.
Yes, and can you try again?
Is this working now? There you go. That's much better. But I don't need to repeat myself. Yeah, you all heard it. Okay, so we have a good workshop and a number of good presentations. So happy to be here with you. You see our list of organizers here. Goethals and Konstantin and Alex Tujilin could not be here with us, but they will be part of the organization, and I think some of them are going to participate remotely at the conference. Moshe and I have been here, and of course he's running the workshop here because I have to run back to the doctoral consortium after this for a little while. Okay, so we have a couple of keynote speakers in this afternoon in the workshop. It should be very interesting. Marius Fragkoul is going to talk about leveraging large language models for sequential recommendation. Obviously, a very important and current topic. And so I'm certainly looking forward to seeing that presentation. And Natalia Silberstein and Jan Hartman on enhancing large-scale recommendation systems with context-based models, and they're from Outbrain. So we have two sort of industry groups of people that are going to be speaking. So looking at practical aspects of context-aware recommendation. And in between these, we're going to have 5 papers, which have been selected. I think we had quite a few submissions. I don't know, 10, 12, something along those lines. Is that right? So we selected these for presentation at the workshop. So look forward to hearing those. And for the speakers, there's going to be a 3-minute Q&A at the end of each presentation. And Moshe, correct me, how long do speakers have for presentation?
Total 15 minutes.
15 minutes? Okay. And you can also ask questions via Zoom chats. We'll monitor those and then ask over here. And all the material and presentations are going to be available on the website for the workshop, which you can access from the RecSys 2283 website. Okay, so I think without further ado, I'm going to turn it over to Moshe, who's going to introduce Marius.
So good afternoon, everyone. My name is Moshe Unger. I'm from Tel Aviv University. And today, as Bamshad mentioned, we have very interesting two keynote speakers from the industry. So I would like to start with the first keynote presentation of Dr. Marius Fragkoul, and he's a senior research scientist in delivery, and is leading a team in recommender systems. He was previously an assistant professor in the University of Ioannina in Greece, and a postdoc researcher in a position in the Delft University of Technology. He also served as a technical advisor at Hazelcast, and his main kind of research includes recommender systems and personalized and session-based recommender systems, contextual information, evaluation approaches, and scalability. So without further ado, Marius, thank you for joining us today. It's going to be a very interesting talk. Thank you. Interesting short here. Sharing the screen.
I don't have to
Yeah, no, just.
Okay. Right. Okay. So thank you for the kind invitation and the nice introduction. So I'm Marius. I'm with Delivery Hero Research, and today's topic revolves around large language models and the sequential recommendation problem. So these two aspects. Well, it didn't occur to me to arrange the title as the title of our paper in the late-breaking results track. That's totally coincidental. My talk will comprise two parts. In the first part, I will introduce the sequential recommendation problem, refer to known variants of that, and refer also to the families of approaches that have been used to solve the problem. And also, I will provide an overview of research with LLMs in recommender systems. In the second part of the talk, I will present our paper in the late-breaking results track. Finally, I will provide a brief account of projects with large language models in Delivery Hero. So, the sequential recommendation problem. An informal way of defining that is that given a sequence of interactions, the aim of the problem is to predict the next interaction in the sequence. So given, for instance, a very ugly basket of items, which comprises a tomato, followed by a cucumber, followed by an onion, we want to predict the next interaction, the next item that will go into this basket. By the way, any ideas to what we are trying to make here with a tomato, cucumber, onion? Greek salad. So yeah, we have Greek people here. Okay, so the next interaction could be or should be olives, feta cheese, and oregano. That's the prime ingredients of Greek salad. Okay, so going forward with a more real example, and since we are at Singapore, we might want to get food delivered by Foodpanda, right? And we might opt for a nice bucket of chicken nuggets, which is proposed to go with a nice side dish, right? So you can see the frequently bought together recommendations, spaghetti, rice, and you can see how there can be an intuitive sequence in this use case, right? We have a main dish that can be followed by a side dish, and that's completely reasonable. To take this a step further, if we add to this first interaction fries as a side dish, now the sequence becomes a lot less intuitive. So what could come next? Would it be a dessert? Would it be another main dish or another side dish? And this is a small indication of how quickly the problem can become a lot more challenging. To make this a bit more worse, frequently bought together does not necessarily imply an intuitive sequence of items. It might do so in terms of in the domain of online food delivery, where we can think of an intuitive sequence as a main dish followed by a side dish followed by dessert, and it can be others. But in domains like movies, there is not necessarily an intuitive sequence behind watching two movies, one or the other, except maybe for sequels, and some might argue Barbieheimer, right? That has been a debate. All right, so the sequential recommendation problem is sequence aware, but it's in its sequentiality, the input is typically organized as a single matrix of user item interactions. There is not necessarily sequence of interactions belonging to a session. It's just a flat time-stamped sequence. Now, two known variants of the sequential recommendation problem are the session-based one, where we do have sequences of interactions, but we do not know the user behind those interactions. Maybe because we don't know the user, it's not a logged in user, or it's the first time that the user is logged into our platform. So no long-term information is available. A final well-known variant is the so-called session-aware, which can be thought of as a combination of the other two. So we do have sessions, so sequence of interactions, and we do know the user behind those. So it's an opportunity to combine the short-term user intent in cars, workshops terms, the interactional context, with a user's long-term user profile. Okay, so in the progression of years, different families of approaches have been used to solve the sequential recommendation problem. Most prominently in recent years, neural-based approaches. For instance, Bert-Forek and Sasrek are landmark papers. They have covered a lot of ground, made a lot of progress. This family of approaches also includes Group4Ek, which is another strong baseline. Other families of approaches include neighborhood-based models, such as SKNN, and Markov decision processes like MDP. One notable observation here regards to the design perspective of these models. So, for instance, Bert-Forek and Sasrek are sequential recommendation models. They have been designed to take this flat sequence of timestamped interactions, while Group4Ek, SKNN, and MDP are session-based models. So their rationale is to consider sequences of interactions belonging to sessions. Now, taking the sequential recommendation problem, it is not too difficult to see how that relates to the next word prediction problem from the natural language processing community. Instead of having, for instance, a basket of items and wanting to predict the next item in the basket, we have a piece of text composed of words or tokens, and from this sequence of tokens, we want to predict the next token or word in the sequence. The next word prediction problem apparently has provided a lot of the inspiration adopted and further developed in the sequential recommendation problem, in the sequential recommendation community. So the gated recurrent unit provided the inspiration for Group4Ek, the transformer architecture provided the inspiration for Sasrek, and the BERT provided the foundations for, for Bert-Forek. Right, and this natural close relationship between the two continues to grow and evolve, taking it to the level of large language models. But before coming to that, I would just like to point out that the whole discussion of sequential recommendation is a strong assumption that we should take into account depending on the domain that we are doing research or practice. So the mere concept of sequence might be ultimately important in some domains, but also rather unimportant in others. Which brings me to large language models, right? And one way that large language models can be thought of is as a large-scale incarnation of the transformer architecture. So they are trained on huge volumes of natural language and programming language corpora, and maintain billions of parameters, which correspond to billions of neural network connections that attend to some piece of the context of text in this particular situation. And this machinery enables them to identify the context of the communication and often provide remarkably well-structured and meaningful in many occasions response. While all they do time and time again is ask and predict which token will come next. So large language models encapsulate a broad representational context, again in cars workshops terms, as broad as the corpus, as the training corpus that they have been trained on. Okay, so in recommender systems research, large language models have appeared in the recent years So from 2021, there has been an array of papers covering research with LLMs. And the first surveys also appeared that try to map and organize this landscape. So what I will do in the next few slides is not go through a mini tutorial or an in-depth investigation, but rather try to surface interesting aspects that regard the involvement of LLMs in recommender systems research. And the figure that you see here is taken from the first of the two surveys, so reference number 8. And it groups the pieces of works on LLMs regarding the stage of a recommendation pipeline that they appear in. So these surveys propose a few categorizations, and I picked one to go with and structure the rest of the content, which pertains to the recommendation pipeline stage where an LLM is involved. And that categorization is shared between both surveys. So in this categorization, there are two main categories. One is LLM embeddings that are then input to a downstream recommendation model. So an LLM encodes item features as embeddings. And the second category is when an LLM is used as a recommendation model in itself. With respect to the pipeline stage categorization, so the figure that you see on the top right, the first category, so the LLM embeddings, appears in the stage of the feature encoding stage, while in the second category, appears in the scoring or ranking function stage. Okay, so going forward with the first category, where an LLM encodes item features as embeddings, these features are, as you might expect, regard metadata of textual metadata of the item domain, so title, description, rating, and other types of context. And it has already appeared in many domains, such as e-commerce recommendations, news recommendations, and web search ranking. And there are many more. And if you want more information, you can, of course, go into the references. The rationale there is to embed these features and try to produce a ranking of recommendations. So, for instance, for web search, both search queries embedded. On the other hand, the title and summary of web documents are embedded, and those are correlated with each other such that a ranking is produced that matches the web documents to the search query as closely as possible. The second point that I want to make for this category regards a core requirement that is embedded into using LLM embeddings as into downstream recommendation models. So the LLM embeddings, in order to be input to an existing recommendation model, the embeddings have to match. So there is a core requirement there of adapting the dimensions of the embeddings. And in order to achieve that, various pieces of work have employed various forms of projection layers in order to make that happen. So those projection layers can be a single layer neural network, a self-attention layer, and other layers that you see here. But what is particularly interesting about this practice is that these layers do a lot more work than just adapting embedding dimensions. And that is the most interesting part. So what they do is basically try to generalize and further adapt the embeddings for cross-domain recommendations. And this is where a major contribution of the LLM models into the sequential recommendation problem takes place. Instead of having ID-based features, while we did in traditional recommendation models, we now have textual features with a broad semantic interpretation of the items. And because of these rich semantic foundations, those features can be used to provide the basis for cross-domain recommendations. So, for instance, the single layer neural network adapts item features for zero-shot recommendations. The self-attention layer takes care of encoding features of multiple modalities. The mixture of experts layer smoothens the semantic representations such that they are more uniform to the for cross-domain recommendations, and the vector quantization-based approach distributes the embeddings to the embedding space in an optimal way, such that the embeddings themselves are more distinguishable and can be used for cross-domain recommendations. Which brings us to the second category, where an LLM is used in itself as a recommendation model. The problem formulation from the LLM's perspective can vary, and there are three different problem formulations stand out. The first one is as an item scoring task, where the LLM is asked to produce a score for its item, and that can be done in two ways. The first way is implicitly via its system design, so that there can be a projection layer at the end of the network that maps the output of the last layer into a space of scores for an item. The second way is explicitly via prompt instruction, which means that the LLM provides a conversational interface where we can basically ask the model to explicitly provide the score for an item. Obviously, item scores can be transformed to a ranking if we just compare the scores for the items. But we can just formulate the problem as a ranking generation task, where an LLM can be asked to recommend tasks with respect to recommend items with respect to an input set of items, which is the sequential recommendation problem, or in the sense of a direct recommendation task to be provided explicitly the items that it has to rank. Complementarily to the previous two, the LLM can produce an explanation for the output it produced. The second point for this category that I wanted to make is that it might imply a further training approach for the LLM. And there are three opportunities here. So the zero-shot approach does no further fine-tuning. The zero-shot approach implies no further examples to the LLM and no further adaptation. The LLM just takes a task and just makes a recommendation from the foundational training that it has received. The second opportunity is few-shot prompt engineering, where an LLM is given a few examples in line to the context, and it temporarily learns how to perform better that task, which is called in-context learning. Finally, fine-tuning is a process that precedes the actual performance of the task, and there the model permanently learns how to perform a certain task through prompt completion first. Right, and this basically summarizes the discussion over LLMs in these as taken from these surveys. Now, you might have considered that a large array of LLM papers appear in this year's conference, and what I try to do here is provide a mapping between the papers and research aspects in the RecSys community. So, for instance, papers 1, 2, 4, and 8 consider sequential recommendation. Papers 5, 6, and 9 consider conversational recommendations. Papers 7 and 12 use the LLM as a recommendation model, like I discussed previously, and the paper number 3 studies the fairness of a large language model. So it's clear to see how research with LLMs touches upon many interesting aspects in the RecSys community. And this completes the first part of the talk. So in the second part of the talk, I will present our paper in the late breaking results track. This is joint work with Yessenalina, who is among us. Also, Wouter Zogdrager, Panos Louridas, Asterios Katsifodimos, Dietmar Janak. Yeah. So the motivation for this paper stems from 4 angles. The first angle is that we wanted to organize and structure the ways that an LLM can be leveraged in the recommendation problem. The second motivation stems from our desire to position research with LLMs with respect to their performance compared to the recommendation models that stand out, so traditional recommendation, existing recommendation models. Thirdly, we wanted to examine how underlying characteristics of the LLM affect the recommendation quality. And since this is a topic of growing interest, we want also to discover further avenues for research. So the approaches that we organized are 3. The first one is to use the embeddings of an LLM combined with KNN search in order to provide recommendations. The second one, in the second approach, we fine-tuned an LLM in order to produce recommendations as a recommendation model itself. And in the third approach, we used embeddings coming from an LLM in order to initialize BERT work. Approaches number 2 and number 3 fall under the categories of the surveys that I described before. Our contributions and findings are the following. So, as I mentioned, we propose 3 orthogonal methods for leveraging LLMs for recommendations. Secondly, we find that BERT4X initialized with LLM embeddings outperforms existing recommendation models. And third, we find that the approach with LLM embeddings combined with KNN search can lead to surprising performance depending on the dataset at hand. To dive a bit deeper into the approaches, the LLM embeddings model combined with KNN search, which we devised with the motivation that we wanted to recommend semantically related items with respect to the items in a session. So this approach, for this approach, we first took the catalog of items, think of a product catalog, and we retrieved the embeddings from the embeddings API of a large language model, in this particular case, GPT. So we retrieved the embeddings of the item catalog. Then for each session that we wanted to predict the next item, we retrieved the embeddings of the items in the session from the embeddings API, and we computed the session embedding. We computed the session embedding in 3 ways, in one of 3 ways, either by averaging the embeddings of the products in the session, or by computing a weighted average of those using a linear or exponential decay function, and thirdly, by considering only the embedding of the last product. In the last step, we compared the session embedding with the embeddings of the items in the item catalog and chose the products with the closest embeddings to the session embedding as recommendations. In the second approach, where we fine-tuned a large language model, we wanted to do that in order to assess the impact of injecting domain knowledge to the LLM. So what we did is take a history of training sessions, and for each session, structure that as prompt completion pairs, where the completion is the last item in the session, and pass those prompt completion pairs to the fine-tune API in order to have a fine-tuned model. At the test phase, we passed all of the interactions of the test sessions minus the last item to the fine-tuned model and retrieved recommendations. So 2 notes that I want to make here is that by design, of course, we expect the LLM to produce hallucinated recommendations. In our experience, that regarded metadata of the product. So for instance, instead of recommending a burger of 200 grams, it might recommend a burger of 100 grams. And we resolve those hallucinations by mapping back to the item catalog through the embeddings. So taking the products with the closest embedding to the embedding of the hallucination, the hallucinated recommendation. The second note that I want to make here is that the LLM model also produced duplicate recommendations. So yeah, duplicate items in the recommendation slate. So here, because we didn't formulate the task as a ranking task, so we didn't explicitly ask the model to provide a ranking list of recommendations, we interpreted the duplicate recommendations of a model as a matter of confidence of the model towards the recommendation. So we ranked those duplicate recommendations higher in the list. And again, we filled in the missing spots in the recommendation slate by mapping those duplicate recommendations to their closest products in the item catalog through the embeddings. So we had the final list of recommendations. In the third approach, we used LLM embeddings in order to initialize BERT for egg. And the motivation for that was that we wanted to leverage the semantic depth of the LLM embeddings into an existing recommendation model, like BERT for egg. So what we did here is, again, ask the embeddings API to provide us with the embeddings of the items in a session. And then going back to the discussion, the first part of the talk, we had to adapt the dimensions of the LLM embeddings into the dimension of embeddings that BERT for egg would accept in its embedding layer. For this, we used the principal component analysis in order to compact further the learned representations of the items, and we input those embeddings to BERT for egg's embedding layer. Then we trained BERT for egg as usual. In the testing phase, that's no different than BERT for egg itself. We just asked from BERT for egg with the embeddings to produce recommendations. So this concludes the discussion of the approaches. In the experiments, we used two datasets. One is Amazon Beauty, preprocessed with the P-core methodology, and the proprietary delivery hero dataset comprising anonymous sessions. We split the data temporally, so we have a completely separate training sessions from test sessions. And for test sessions, we leave the last item out as a prediction target. With respect to recommendation models, we used BERT for egg, SASREC, Group for egg, SKNN, and Popular, besides our own approaches, for which we did exhaustive hyperparameter tuning, and we also verified the performance of our implementations with respect to the original papers. In terms of metrics for ranking accuracy, we used NDCG, MRR, and hit rate, and for beyond accuracy, catalog coverage, renditivity, and novelty. We used 3 folds in the hyperparameter tuning part and used NDCG at 20 as the optimization goal. A few words about the data characteristics. Obviously, these datasets are highly complementary in terms of scale, in terms of the average length of sessions, and also in terms of density. Also, in the plots, you can see how the pre-processing, the presence or absence of the pre-processing methodology makes a difference with respect to the long tail in the popularity distribution and the magnitude of sessions with few items at the left of the session length distribution. Going on to the experimental results, I don't expect you to read this, but I just want to point out that LLM to BERT for egg is our approach where we use LLM embeddings in order to initialize BERT for egg. LLM sec-sim for sequential similarity points to our embedding model combined with KNN search, and LLM sec prompt for sequential prompt points to the fine-tuned model. We use the cutoff points at top 10 and top 20. So I want to make 4 specific points about the results. One is that LLM to BERT for egg prevailed over the other models in terms, so by 15 to 20% in terms of NDCG at 20. So it was the best for all metrics in the delivery hero dataset. In the Amazon Beauty dataset, it was challenged in terms of MRR and NDCG at 10 by the embedding model. And this is the next point I want to make. So the embedding model did show a surprisingly good performance in the Amazon beauty dataset. Yes. Right. So, in the other, so in the Delivery Hero dataset, its performance was mediocre. Nothing to report there, nothing to comment. With respect to the Delivery Hero dataset, it will come. Okay, maybe I'll come back to it. Problem. Okay, so for the fine-tuned model, what is interesting to note here is that its performance falls very closely to what we consider very strong baselines, like for instance, even state-of-the-art model, like SASREC and GRU4Rec for the Amazon beauty dataset. And while it trails behind the other state-of-the-art models and strong baselines in the Delivery Hero dataset, still its performance is markedly better than the popularity baseline. Which brings us to the beyond accuracy metrics, where the embedding model had the best metrics with respect to catalog coverage and novelty. This is not too surprising if we think that the power of the LLM embedding model comes from the semantic representation of items, and it's not at all influenced by the collaborative signals of the interaction, which are biased by the popularity of items. With respect to serendipity, this follows closely the ranking accuracy metrics, where LLM to BERT for egg is best, and this is expected if we think that it's normally better to provide personalized recommendations rather than recommendations based on the popularity of items. Follow-up opportunities for research. We would like to explore whether these results generalize to other domains as represented by datasets, and whether they generalize to other large language models. Secondly, we would like to combine LLM to BERT for egg with the embedding model in order to try and bring the best of both worlds in terms of ranking accuracy metrics and beyond accuracy metrics, and also consider whether richer embedding, so if we consider product categories, descriptions, and reviews, for instance, will lead to better performance. From an industry perspective, there are a number of projects regarding large language models in Delivery Hero. These broadly fall under two categories. The first category regards recommendations by leveraging LLMs in the pipeline, like the context of this work. And the second one regards conversational search and recommendations, where we want to tackle two main research questions. One is how to best adapt the model to the domain that we're doing business with. And the second one, how to create a safe model, so a model that can actually interact with users. And with this, I thank you, and I'm open to any questions you might have.
So like,
Sorry.
could you please unmute the Zoom so remote can't hear us?
Yeah, thank you for the talk, very interesting. So can we go to approach one for the embedding method?
Sorry, one moment. Ah, it's up, but it's unmuted. This one?
On the Zoom, is it like already connected to the Zoom? Oh, Zoom, are you muted?
I'll do that.
I have submitted a card or something like not similar to what I already had, right?
Can you repeat the question?
Yeah, so I mean, the second question is about like the choice of using similarity for next item recommendation. So if I already added burger in my cart, I don't want to add another burger.
Yes.
So the next item I want is not similar, shouldn't be similar to what I already have in the cart, right?
Yes. So the question regards the intuition and the semantics of similarity. So, for instance, in this particular use case, an example would be that if there is a burger in my basket, I don't necessarily want another burger. Yes, as an intuition, it does absolutely make sense. It's one of the It's one of the aspects that we continue to experiment with for our use case. But the main thing that we wanted to make public with this work was the different approaches involving LLMs for the sequential recommendation problem. So this was the focus of our paper and not the particular use case and what would make absolute sense for that. But I agree with your intuition, yes.
Thanks.
Yes. Thank you for the very inspiring talk. I have also a question regarding these embeddings, since well, there is this interesting phenomenon that you have presented where on the Amazon dataset, you have decent results, and on your own data, the results are like average.
Yes.
So what I wonder is whether there is a chance that the ChatGPT embeddings were just ingested or trained with the data that you use it for evaluation.
Okay. Right. So what you mean actually is that the LLM already had a very strong intuition regarding the data that we actually had to ingest and experiment with in the Amazon Beauty dataset. Yes, that's one plausible explanation. But okay, and now I remember what I wanted to talk about in the main part of the presentation regarding the embedding model. Is that what's interesting there is that the way that we computed the session embedding for this particular dataset is that we only took into account the embedding of the last product. So the semantics of the last product proves to be decisive of the next item that will be put into the basket.
Okay, thank you.
Thank you for interesting talk. If I understood correctly, Bert-for-Ek with LLM embeddings has lower category coverage than original Bert-for-Ek. Why do you think it happens? And is it okay that Bert-for-Ek with LLM embeddings has lower category coverage than original Bert-for-Ek?
Okay, so the question is the observation that actually Bert-for-Ek, the original paper implementation, has a lower catalog coverage than the Bert-for-Ek when it's initialized with LLM embeddings, and whether that's troublesome or a problem. Okay, so but wait, so you compared Bert-for-Ek with LLM embeddings, right? But catalog where catalog coverage is higher for the Bert-for-Ek model. Okay, right. So to be honest, we didn't particularly dived into this this distinction between the two. If I have to think about it out of the box, I would say just guessing here that maybe there are aspects in the embeddings, in the LLM embeddings, that make Bert-for-Ek to focus towards more specific parts of the catalog rather than the ID-based embeddings that the original model normally ingests. But we didn't dive into this, so I don't have an educated information why this happens.
Thank you for your talk. And my question is, have we studied the distribution of LLM embedding, and what information does the embedding actually contain? For example, is the embedding of like a pizza much closer to the embedding of a pasta than to the esprit?
So, sorry, could you repeat the question?
Okay, so have we studied the distribution of LLM embedding, and what information does the embedding actually contain?
So the question is whether we have studied the distribution of LLM embeddings. Yes, would you like to? I don't remember the specifics.
Yeah, so I've done this for the computing data set. What you can see from the recommendation from LLM is that it mostly focuses on brand names.
Yeah, so I did a small analysis for this on the Amazon Beauty data set. And there the LLM sequential similarity model indicates, from those recommendations, you can see what information do these embeddings contain. And in that case, we could see that the model predominantly focused on the brand name of the products, and to a lower degree on the inherent type. So yeah, this is spaghetti and pizza.
Thank you.
Thank you, very interesting talk. So I guess I have a question. So I think in your work presented here, the main contribution is you replace the original ID with some kind of semantic understanding gained from the large language model to represent the items in it, right? I'm wondering, have you tested out how important the model size will impact on the performance? So which version of large language model did you use? How the different size of large language model impact the final performance?
Right. So the question is, to which extent the size of an LLM influences our results, and whether we have studied this. We didn't actually have the time to consider different LLMs or different versions of an LLM concerning the size of the model. So it's it's one of the many aspects that we would like to follow up with. So I don't have any further information on that, unfortunately.
I see. And also to echo the question coming from the previous kind of the other people, I'm wondering, have it occurred to you, because large language model is trained with a lot of public open corpus from the internet. So the public data set we'll be using may be just used in training that large language model, and thus causing information leak when you are leveraging this information.
That is true. That's an accurate point. So the point is that, question actually, that the Amazon Beauty is a public data set. It might well have been in the training corpus that the underlying model that we used was also trained in. We did not. So one nice, but how good. So I do not know the answer to this question. So there is indeed a high possibility that the Amazon Beauty data set was actually in the corpus, in the training corpus. I do not know whether it was or was not. Probably it was. Yes, and but then I would expect, now that's another kind of guess, I would expect that the influence of this data set would be lost in the statistical aspects of the training of the LLM, being only one data set in a billion of others. But that would be my my guess here.
Okay, thank you.
We don't have time for more questions. Thank you. You can go offline. I will thank you for presenting an amazing work. So let's thank the presenter again. Thank you, Natalia. And I know this kind of topic raises a lot of questions, interesting questions. So feel free to reach Marius and the team, the research team behind him later, and take some of the questions also offline. I have like lots of questions about other types of context, like how we can integrate more like contextual information, such as weather, other kind of contextual factors that really influence user intent, in terms of would it be possible to do it within the system, or kind of different embeddings only for context and then integrating it into the system. But we'll take it offline later to discuss that topic. So let's move to our paper session and start with the first presenter about weighted tensor decomposition for context-aware collaborative filtering. This is a work by Joey de Pauw and Bart, and the presenter can come and thank you. And let me just make sure everything is, that's mine. Can I go full screen for the presentation? Yeah, you can do whatever you want. Yes. Maybe. You're right. I try it for them. It's really close. Okay, I'll just go lines. Yeah.
So, hello everyone, my name is Joey de Pauw, and I'm excited to be here to talk about my work on weighted tensor decompositions for context-aware collaborative filtering. In this work, we study different aspects of tensor decomposition to consider for the cars problem. First, I will go over a brief introduction and introduce some notation. then go over the different methods, and finally highlight the most important experimental results and list the conclusions and future work. Get started. Typically in collaptive filtering, we assume a sparse input format, which is a matrix we often call X. This contains a 1 for every user item interaction, and all of those are zeros or unknown. And the task here is to predict a relevance score for these missing values. And based on this relevance score, we can then again create a top K list of recommended items for each user. Now, if we extend this to the context-aware recommender system problem, we would assume that we can extend also this format into a tensor. So for each context, we can add an extra dimension, and then every interaction becomes a 1 for every user item and context pair. This already presents us with the first choice, namely we can put every context within its own separate dimension. I only visually represented 3 in this slide because higher dimensions are very hard to illustrate. And so by doing multiple dimensions for each context, you can actually also model the interactions between the contexts. There's a second option here that's stacking all of the contexts behind each other. And then you would have multiple entries, multiple ones for each interaction happening. But the format is a lot less sparse, and you also lose a bit of capacity to model the interactions between contexts. But this might not always be needed. Then to approximate these, the missing values and compute the relevance score, we look into low-rank approximations. For matrices, again, this is quite well known to apply matrix factorization, where basically we take 2 lower-rank matrices, the user and the item vectors, and the dot product between these 2 gives you a relevance score. However, for tensors, there's not one straightforward decomposition method. There's actually a lot out there. I will show the 4 most popular ones, perhaps. First one is the CP, or the Canacom parafact decomposition. In this one, we extend the idea of taking dot product between vectors, and we go towards a 3rd order dot product, I call it. This is basically just the element-wise multiplication of all the entries in the vector and then the summation. And so we have user vector, item vector, and context vectors. Then there's also another format called pairwise interaction tensor factorization, or PITF. As the name suggests here, we do not take these higher order dot products, but rather we take all of the pairwise combinations that are possible and then sum them up. So you take the user item product, user context, and then item context, and everything is summed together. Then a bit more recent decomposition method is the tensor train factorization. In this case, we do not have vectors for all of the entries, but rather we chose to model the context as matrices. And so a single prediction here is actually the product of a row vector for the user multiplied by a matrix for the context, and then finally multiplied by the column vector for the items to again get a single value for this prediction. Important note here, if you go to higher dimensions for tensors to factorize, you just get more matrices in the center, and they're all 3rd order, rather than the Tucker decomposition is a bit different. Here the use core tensor, and this core tensor scales in dimension with the dimension of the input format. So we already listed 2 choices to make. First, the tensor structure to consider, where you can go up to 3 dimensions and just stack all of the contexts behind each other. This is the first column in the table over here. Or we can go multidimensional, where each context gets its own dimension. Then there's a lot of tensor decomposition methods. We only study CP, PITF, and the tensor train factorization. And we already found in literature that for CP and PITF, there were already methods published that use these, namely ITALS, ITALS-X, and then the fast tensor factorization for multidimensional here. We introduced ourselves the weighted tensor factorization, WTF, that uses tensor train formats. And we also, in our experiments, maybe I should first say this, the loss function we are considering is a weighted square loss function. This is really useful because it can be optimized with alternating least squares, which is very efficient, can be parallelized, and leads to nice embeddings. And this is just square loss with an additional importance weighting, so you can give the missing values less importance within the loss. And then some regularization is added as well to regularize all of the factors. And typically, we want to pull all of the factors towards origin or towards a 0 vector. And this is what all of these methods do. But we found in our experiments that sometimes it makes more sense to model the contexts a bit differently, to give them a less important role within the recommendation problem. Rather than having them as equally important entities as a user and item, it makes more sense sometimes to model them as offsets towards an already established user item prediction. And to this end, we introduce the one-based regularization or the identity-based regularization. Well, these methods suffixed, with a one behind them are the methods that use this new regularization. Let's perhaps make it a bit more concrete. For each of the decomposition methods, I will show what this would look like. So in this case, we can imagine that if nothing is to be learned from the context, if it has no impact on whether the user might like an item, if they just like it all of the time and there's no time impact on it, then we would perhaps want this BC to not be equally important. And so rather than pulling it towards the origin, we actually want to pull this towards the vector of ones, because then in this dot product, it will just multiply element-wise by the one value and it will not have an impact. And so the loss does not have to pay for the fact that there's nothing to be learned from this interaction. And we fall back to the default user item prediction. For the pairwise interaction tensor decomposition, then we can see that regularizing towards 0 is exactly what we want, because if BC is 0 in this case, then the the second and the third term will be dropped, and then we fall back again to the user item prediction. And finally, for tensor training factorization, we find that BC has to be the identity matrix for it to not have an impact, and so we regularize it towards the identity matrix. There we go, that's all the methods. Let's then look at the experiments. We studied 3 publicly available data sets. I will only show the results for the Frappe dataset for to be concise. And for the experimental setup, we take leave one out cross-validation. And we also make sure that every user and every item has at least 3 interactions within the data set. For metrics, we look at the mean reciprocal rank and the hit rate, both at 5 and 20. Mean reciprocal rank is a ranking metric, and hit rate is just a 0 or 1, depending on whether the item is in the tested item is in the prediction list or not. Let's first look at the baselines. These are just context unaware methods that do not use context information, just make the prediction purely on the user and item parts. We find here that the WMF method performs best, which is great news for us, because all of our methods are based on this the same loss. Then all the flattened models, I have the values over here. We can already compare the 1 version versus the 0-based regularization version. And here we find that the 1 version always outperforms them, also on the other data sets. So this strengthens the hypothesis that context should be more of an offset rather than the equally important entity. And then finally, for multidimensional, the first thing we find is that the ITALS model was not able to capture all of the information within this data set. It's, of course, even worse than the context unaware baselines. And a simple explanation for this is, if you recall, it uses the CP decomposition methods. So in this case, I have a 5th order dot products, and 3 of those are the context, and then only 1 using item parts. And so the context just outweighs this prediction. And since we're doing a top K recommendation problem for users, we get such poor results. And if you then compare the multidimensional versus the flattened version, again, find the flattened version. Well, in these data sets, they're very close together. And the other 2, the flattened version works a lot better. And so it's usually just not necessary to go towards modeling these dependencies between contexts, because the dimensionality increases and you need more data to actually model them. Then we also did a second set of experiments where we start from already established user and item vectors, just learned by WMF. And then in 1 iteration of the ALS, we learned the context vectors. So the user and item vectors are unaware of any context information. And then post hoc, we try to add it to simulate, for example, a use case where you already have an embedding-based system in your company and you want to see whether adding this context information would make sense. Then you can quickly set this kind of experiment up. Here we find, well, first that ITALS improved a lot, but it already performed so poorly earlier, so we should really not look at it. And the clear winner here is the WTF, weighted tensor factorization, which demonstrates that it's a lot more expressive because we use an entire matrix to model the context. It can actually learn more complex transformations for these vectors, whereas the other ones only use a vector for the context, so they can only scale it along the axis already established. So for conclusions, we study weighted square loss models, which have a lot of very good benefits. I hear that they also used a lot in industry. And these are their extension for context-aware models. We mark the importance of the tensor structure, how you decompose them, and most importantly, how you regularize these factors, and show as a bit of a guideline, depending on your use case, which options you should take. And perhaps the thing I'm most excited about is that all of this can be extended to learn from continuous features as well. I don't know how I'm doing on time. Can I? 1 minute? Oh, that's perfect. So in my future work, I want to study how we can model continuous features. And typically this is done by, for example, let's say time here, the most prominent continuous feature, by binning them together. This could, for example, be the day the interaction occurred on. And then we can learn embeddings this way. But actually they will not look like this because we can expect there's a high dependency between different days. So things that happen close together will probably have a similar embedding, and we can get this more smoothened out embedding over here. But then the problem becomes, if we want to go more fine-grained, we can learn for every hour perhaps. We lose the signal because perhaps there's not enough data to make the connection between them, and we again do not get this smooth connection between the vectors. Typical solutions will use, for example, a decay function, can be a Gaussian, sigmoid, whatever, to smear out the interaction over multiple time steps and then learn from this. Only problem here is that it becomes a lot more complex to learn from because you have your interaction becomes a lot more often used. And so what we have figured out is that we can actually keep this time signal as a discrete event and still learn continuous features. And we can even not sample them, we can just learn them fully continuously. So look forward to that. Thank you.
We have time to two questions. If you can repeat the questions of the audience in the Zoom room. Thank you. Any questions?
Thank you. Very interesting talk. I am interested about two things. One, what kind of method do you use for learning? So is it ALS? And if it's ALS, then how does your learning scale the dimensionality of the core tensor?
Yes, okay, so the question is what kind of learning we use. Let's go back to this slide perhaps. Indeed, we use ALS to optimize these methods. And as you can see, we use only CP, PITF, and tensor train factorization. So these are the methods that do not make use of this core tensor, because I'm not aware of any methods that uses ALS to learn the Tucker decomposition. And so they actually scale linearly in the number of users, number of items, and number of contexts, and can also be parallelized, which is nice.
Thank you. And my other question is, why do you think that there is this difference between the results when you use the pre-trained or the one-step item model from the weighted matrix factorization and when you use that?
Yes, thank you. That's a very interesting question. You can, for example, look at the idea that the time when you interact with something or the context under which you interact with something also has an impact on the recommendation. And so within the user and item factors, the model cannot put any context-related information. So for an example, if you go see the Matrix movie, and you go see it when it was just released, it was very popular and everyone went to see it. This is a different signal compared to if you watch the first Matrix movie right now, because mostly the geeks will be doing that compared to just the entire population because it was so popular back then. And so capturing this information is not possible if you do it post hoc.
So let's thank the presenter again. Thank you so much. We are looking forward to see the results for the time series analysis, maybe next year in our next kind of workshop. All right, so the next presenter will present the design principle of robust multi-arm Bandit framework in video recommendations by Amazon Prime Video, and the presenter is Zhen. Let's thank the presenter. Thank you. We make sure.
Please use this one. Okay.
Yeah. Yes.
Yeah, thank you. My name is Jinfeng. I'm from Amazon Prime Video. Today I'm going to talk about design principles of a robust multi-armed bandit framework in video recommendation. So our motivation of our work is some specific unique challenges in the industry recommender system scenario. So our application is trying to promote Amazon own or exclusive video in their homepage. And the importance there is the exploration aspect of the recommendation system, because those titles are new and we want to acquire as much as possible the user's interest, but without sacrificing the engagement metrics, meaning that exploit their known interest. And another aspect is that the promotion basket is usually small, 10, 20 titles at the same time, and each of them will be promoted for like 20, 30 days. So you can imagine that for a new title, the most critical period is the first 1 or 2 days. It will mostly decide whether it will be successful or not. So in this scenario, given the small size of the promotion basket and as well as the short time window, which is critical for its success, and we'll see quite a dramatic challenge, a significant challenge for the data sparsity. So that's why those data sparsity caused some problems in our recommender system. And then we proposed the several design principles to help to address the problem. So just a basic description of what our baseline recommender system is. So here we use a multi-armed bandit to do the exploration part. And the objective is that we use Thompson sampling, use the variance to decide whether we want to explore more or less for a particular feature, given its variance. So the contextual bandits are cheap, but and have promising characteristics, but still they have some instabilities in our particular application. So here is some of the key challenges. So one is the data sparsity. So you can imagine we train our model incrementally every 6 hours to make the model updated to the most recent user interest in the viewing trend. But this gives us instability for the time window changes. So when the feature transition from one time window to another, some of the features, for example, the temporal feature, the time feature hour since launch, because it's a continuous feature, we quantize it to several windows. So when it's changed from one window to another, there could be a big jump in the learned results. So that caused the model instability. So another problem is that our business partners give us some features that we can jumpstart our exploration. For example, marketing category is one of the features to indicate how much the human expert, like a marketing folks, wants to give the priority to a particular title. But the problem is that there could be strong title and the weak title all have the same marketing categories because a human subjective judgment could be wrong. So if a strong title and a weak title occur sequentially, and the strong title may be punished by the weak title because they share the same feature. And yeah, so those are the key challenges for our bandit in the certain application scenario. So how we can make the multi-armed bandit more stable? So here is the solution. We propose the several design principles here. So the first principle is also quite intuitive, is that we want to put on the constraints like L2 weights smoothing, given that we already have several time windows before to train a model of parameters. And we hypothesize that these parameters won't change too dramatically because people have already some initial feedback towards this particular title. So they won't have too significant change from their to deviate from the past, for example, 6 or 12 hours. So this is the one of the constraints we put on the weights change across different training cadence. And the second principle we applied is the data augmentation. So this, we use a certain feature, our since launch as an example. Like I said, so when the title transitions from the 6-hour window to the next 6-hour windows, then we found that for the new, at the beginning of the next 6-hour windows, they may not have much data to train the parameters, so that it may be very different from the last 6 hours. So for the new 6-hour windows, we use the data augmentation technology similar to computer vision research, is that we assume the user's behavior is kind of a continuous. So at the boundary, they shouldn't be as like step function change. It should be a smooth function. So we use the neighboring time window to augment some of the data samples across the two different time windows, so that we have overlapping data samples to ensure the smoothness of the parameters. And the third principle we utilized in the Bandit is the temporal signals specific to each of the promotion window to solve the cannibalization problem. So remember we said some of the titles may share the same feature, like the marketing categories, so that some of the strong titles may be penalized by the weak titles because they share the same features. So that's why we want to have more title level granular information, so that the model can distinguish the individual performance. So here we introduced a new feature called the normalized distinct streams, calculated by the total number of stream of the title in the particular window, like a 3 hours window, can calculate 3 windows together, and then divided by the total number of streams within that time window. So this will give a relative importance, relative to the importance of the total number of streams for this particular title. And another benefit is that we can also make this normalized streams to prevent the kind of cannibalization across different countries. So for example, in some countries, there are more viewers like US, and in some other countries, there are less viewers. For example, like Ireland may have much less viewers. So if we use this feature, it can help the local titles in Ireland to be more robust against the cannibalization from a title, global title. So those are some of the implementation details of the models. I will not go into too details of this. You can always find this in the paper. And we compared the proposed Bandit against the baseline Bandit to see how much we improve. And to compare the performance, we used several metrics, ROC, AOC, PR, AOC, and the aggregated NDCG. So the NDCG is to compare the ranking, is to measure the ranking of the bandits across the time. So here are the comparisons. So the green line is the orange. The orange line is the proposed method with the 3 design principles. And the blue dot line is the baseline models. So you can see it improves all the metrics above the baseline, but you can see overall the change is still not very smooth. That because, like I said, the promotion basket is not that big. So at times there will be new titles introduced in the promotion bucket. For example, if there is another title introduced in this timestamps, or another title exit the promotion basket, so that will cause a dramatic change of the ranking. But our proposed method still keeps the NDCG metrics much more improved than the baseline. So here is additional experiment for experimenting with the L2 regularization, constraints the weight to fluctuate in the smaller range so that the customer experience, so they won't see too much of a change of the ranking. Otherwise, we also got a lot of escalation saying why those ranking changed so dramatically, because for most of the customers, they still want to see some continuity in those promoted titles ranking. Okay, so to conclude, here we propose several design principles to address the particular challenges in the industry recommender system, where we may have unique application requirements, like in this promotion situation, where we have data sparsity and we focus is more on the exploration of individual titles rather than the global engagement metrics. So we demonstrated the three principles, namely the data augmentation, the weights regularization, and the temporal granular signals to help us to improve the stability of the recommender system. And then we show that we have quite satisfactory relative improvement of the AOC numbers, 12% and 44%. And so the future work part is that we hope we can generalize those design principles from the multi-armed bandits to other ML framework as well. Yeah, I think that's my presentation. So any questions?
Thank you for your great presentation. I have two questions. So the number one is you showed a significant positive improve on the offline metrics like NDCG and UC. Did you try to launch some online experiments, and did you get such significant results as well?
The question is, we showed the offline analysis in the presentation. Have we done the online experiment? So the answer is yes. So the online experiment came in much later, after the paper submission. So basically what we did is the web lab, by having all those design principles to compare with the baseline. So what we observed is that we, of course, in the online A/B testing, we're tracking business metrics, like this number of promoted streams, whether they increase, and other things like whether the engagement metrics got penalized. So we track those things. So the finding is that for engagement metrics, they are flat, which is our expectation. And then we have increase of the promoted streams, which is also a positive metric for us. So that's the first question. Yeah.
Thank you. And another question is, it seems to me that this whole process is quite similar to counting co-star. So yeah. Do you think there is any differences between the goal of counting co-stars and the business goal?
The question is, this process is similar to content co-start, and whether we have similar goals with content co-start and business goals. I think my answer is yes. This is actually a content co-start problem, but for business metric, they have different, more granular business metrics goals. Because like I said in the presentation, they have the content marketing categories, meaning that they divide those content into different categories, and for each category, they give different priorities, meaning that they want to allocate more impressions to promote a higher priority rather than lower priorities. And some of the priorities may be subjective. So it creates a challenge for the system, meaning that for example, some of the executives want to promote a certain title, maybe weaker by the audience feedback, but they still want to give more resources. So that will kind of will be challenging for keeping the engagement metrics. So those are the fine details of the business goals.
Thank you. That's very much.
Yeah, it's working.
Okay, thanks for the great talk and the presentation. Actually, my question is a follow-up to the other audience regarding to the lab experiment. So by running this Bandit exploration, the model also like affect the popularity of items in your treating marks. So when you run the online experiment that you mentioned, engagement neutral, there's positive metrics side. Do you have any tricks to isolate this indication and evaluate the expanded approach by itself, like isolate those like popularity shifts?
So the question is whether we can isolate this popularity factor to do the online experiment. We haven't thought about this direction yet. So one of the reasons is quite practical is that we have a limited time to do online A/B testing, and also the each testing for us will last 4 weeks, which is 28 days. So the practical constraint make us to test as many changes as possible in one experiment, so that it's a little bit hard for us to separate them into different experiments. But this is a good direction. It's just we are unable to do that right now. Yeah.
So let's thank the speaker again. Thank you.
Yeah. Thank you.
So we're going on a break right now. So just quick notes. Again, we have all the presentations and the papers ready to be uploaded or downloaded, sorry, in our website. So if you want to see them, you can go there. We will be back at 3:50 in about 20 minutes for the Outbrain keynote speakers.
from all the more lighter side, but it's super comfortable and like very annoying. Same one to go to the office and more like 20 bring anything or like with my ball and put toys for him. Have like a slider on the side.
Yeah.
Once
I see the door closed. So we're gonna start on time. Sorry for people who will come in. So I want to present the two speakers from Outbrain, Natalia Silberstein and Jan Hartman. Jan Hartman is a data scientist at Outbrain, and he works on low latency ML pipelines at a large scale. And he's like tackling and implementing and applying state-of-the-art models for click prediction. His research interests include deep learning, neural networks, embeddings, and model compression. And Dr. Natalia Silberstein is a senior data scientist and team leader in the recommendation group at Outbrain. Her responsibilities involve enhancing and developing algorithms for personalized ad selection. Prior to joining Outbrain, she worked as a research scientist at Yahoo, Research Haifa in the native ed science group. So without further ado, I want to invite Natalia and Jan for presenting enhancing large-scale recommender systems with context-based models at Outbrain. I want to also to note that they were accepted to the conference, and their paper is also in our website. Natalia, thank you.
Yes. Hello, everyone. Thank you for the introduction and thank you for the invitation. So today, together with my colleague Jan, we are going to present our work on enhancing large-scale recommender systems with context-based models at Outbrain. So as Moshe already mentioned, a poster related to this work will be presented at the industrial track session on Wednesday. So we will be happy to see you there as well. So today's talk is structured mainly in two parts. So Jan will take the first part, and then I will take over the second one. So enjoy. Jan, the stage is yours.
Okay, thank you, Natalia. Okay. This doesn't work, by the way. Oh, yeah, okay. Let's take a look at what we'll be explaining for the next 45 minutes. So we'll start off introducing Outbrain as a recommender system. Here, the main topic will be industrial CTR prediction at large scale. Next, we'll talk about what context means for us. We'll define context-based prediction models and talk about why did we choose this approach and tell which problems are we solving with it. We'll also demonstrate the results we got using it, talk about a few discussion points, considerations we had to make along the way, and other use cases we have for it. So yeah, let's get started. Okay, so in most services that we use nowadays, our experience will be driven by the recommendations that we get. So Netflix will recommend us movies and series. Spotify will recommend us music and podcasts. Outbrain, on the other hand, recommends the next piece of web content you're going to view, whether it is an article, a video, or maybe even an ad. So as an example, you can see here on the right our widget on the CNN website. And it turns out that we're actually on quite a lot of websites and we reach a huge number of people. As far as I know, this is up to a third of all the users of the web. So that's quite a lot. So maybe let's talk about how the recommendations on the web look like. So on the left, you have an example of a news website with several placements for recommended content, from the banners at the top to the placements and feeds at the bottom. So each of these is personalized for someone visiting the website. So basically, each visitor gets a full page experience that's completely tailored to their preferences. And to make these recommendations happen, we connect two entities, publishers and advertisers. So an example of a prominent publisher, CNN, like Washington Post and a few others that you can see here. For example, advertisers, we work with Samsung, Microsoft, and a few others that you can see here. So connecting these two makes us a two-sided marketplace. So for publishers, for example, we get them what they want, which is engagement, monetization, user experience. And for advertisers, we get them an audience, help them raise brand awareness, conversions, and similar. So yeah, let's show maybe in a bit more detail how do our recommendations look like. So this is a typical flow of our recommendation engine. We have a visitor visiting a website site, and while the page is loading, we serve them recommendations with our online recommender system. Then the visitor might click on a recommendation or an ad and go to another website. And then they might also take action like buy a product or register or sign up for a mailing list. All of these actions are stored and logged in our data store, and our recommender system periodically learns from it. So notice how this creates a feedback loop of sorts. So basically from every visit that we get, it improves our recommender system, and this means that the next visits will have an even better experience with recommendations. Okay, so far I explained like the basic flow. Maybe now let's look at the scale we are working on. So on the web, we serve over 11 billion recommendations every day, and we get over 750 million unique visitors per day. On the back end, our models make over 1 billion machine learning predictions every second, and they are trained on over 100 million examples every day. So this scale is something that we'll keep mentioning because it's really relevant to our problem, and not all approaches can be used because we're working with such a large scale of data and predictions. So I mentioned we have machine learning predictions. Maybe now let's look at what goes into those predictions. So our predictions are used to create better recommendations. The data they might consume is, we can divide it into several categories. On the upper part, we have, for example, the user, so their location, their device, what are their interests. We have the web page the user is on, so which publisher is this, what language is the website in. We have the placement of the recommendation, so where on the website it is, how large it is. We consider this upper category to be context features. So this is something that is given to us in a request that we receive. On the bottom, we have the ad, which is also a very important part of making the prediction. So for example, the title of the ad, the brand, everything here is important. So all of these can be considered that to be features in our machine learning models. And of course, many, many more. Okay, so yeah, we know now what do we use to create recommendations, and now maybe let's consider a bit more detail about this. So one of the most important models that we have in our stack, like most online advertising companies, is the click-through rate or CTR prediction model. So to formalize a little bit, the CTR prediction model estimates the likelihood that a user will click on a recommended item or an ad, to be more specific. The CTR model, as you can imagine, is kind of important for the success of online advertising campaigns, and it also impacts the revenue that publishers, these websites, generate quite a lot. So what does it matter for both sides of our marketplace? For advertisers, it enables them to target their ads to the right audience and get the engagement, while for the publishers, it improves the user experience if we show the most interesting ads where we can. Okay, so needless to say that like having a good CTR model is really important. I know there's a whole section of the RecSys track happening on Wednesday that will talk about CTR prediction. So even small improvements here can translate into millions and billions of dollars of revenue. Yeah, so it is important. Okay, so maybe let's look at a bit more details about how to put a CTR model together. So what are the main components of a CTR prediction model? CTR prediction is a binary classification task. Is either the user clicked on an ad or they didn't. So you could use something as simple as logistic regression for it, or you can turn to something a bit more domain specific. For example, the factorization machine family, like field-aware factorization machines, or deep factorization machines, or even a more recent approach called deep and cross network V2. These are all algorithms that we have or are currently using in our stack. Apart from the algorithm, it's also important how do you train these models. So as I mentioned, as we have an enormous amount of data, we have to take into account that this data is also constantly changing. So you can't just throw away that much of it. You have to account that your model needs to learn the underlying distributions and needs to do so constantly. So two important techniques that we have here are online and incremental learning. So online learning just means that we are continuously updating the model with new data as soon as we get it. So it just means that we are not like waiting for I don't know, like a week to gather a new batch of data and then update the model. It means we do it constantly, specifically every few minutes. Incremental learning just means that when we update the model, we don't want to train it from scratch. That's because it is both too costly and too time consuming. So just incremental learning is a technique where when we can extend the model's knowledge with new data and not have to retrain it from scratch. Again, I'm mentioning scalability because it is really important here. If we make an improvement to the model, we also have to consider what is the cost of serving this new model. Like, did we maybe make a tiny improvement, but increase the cost of serving by 5 times? This will probably not work out in production. So basically, any improvements that we make, mind the cost. Okay, let's now maybe wrap up this section by considering how do we actually use a CTR prediction model. So in short, we use it to rank ads. Now let's explain the scheme in a little bit more detail. So on the left, we have the context features. These are, as we mentioned, the user, the page, the placement. And on the right, we have ad features. These come from a different source. So we have basically just one version of the context. So because we got one request, but we have to consider that there are many possible ads we could show. We have millions and millions of ads in our system, and we filter them to usually rank a few thousand for a given request. So the ads will be probably from different brands, for example, from Microsoft, Samsung, Visa, and Volvo here, and they will have different CPCs. A CPC means cost per click, and it means how much is this advertiser willing to pay to get a click on this ad. So here, for example, like you have Volvo is willing to pay $1. So once we have this, we put this into the CTR prediction model, and we get the probability of the click happening. And once we have this, our ranking score will be a function of the predicted click-through rate and the cost per click. What this means basically is that the ranking score is the estimated revenue we will get if we show this ad. So you can imagine that ranking the ads correctly means a lot because it directly impacts the revenue. So as I mentioned, the CTR prediction model is really important, and now you can see why. So if you have a better CTR prediction model, you'll have more accurate predictions, you'll get more accurate rankings, you'll show more relevant ads, more users will click on them, and you'll get more revenue. So this is in a nutshell like why most online advertising is very click-through rate specific. Okay, so this has been our usual flow for recommendations and CTR prediction. And now I'll hand it over to Natalia, who will explain more about context-based models, which are our new approach. Natalia, stage is yours.
Thank you, Jan. Okay. So what would happen if we trained our models based only on contextual features? In other words, what would happen if we just omit all item features or add features in our case? So by doing so, we expect to capture the likelihood of a click regardless of the displayed ad. Or in other words, with this approach, we could estimate the potential revenue of a specific context. We will see in the sequel why it is so important and how contextual-based CTR prediction models, so models of this type, okay, based only on contextual features, why these models and how these models can help us. So now I would like to provide you some intuition why actually context is so important. So in Outbrain, we experience a very high variance in attractiveness in our supply, where supply is kind of combination of ad placements, so where we show our recommendations, and user audience, to whom we show our recommendations. So imagine that we place some ad at the top of CNN news page and compare it to another placement at the very bottom of the page, where probably user will not get, in some less premium publisher. And by the way, this picture, so this its role is to illustrate this such less successful placement. And now the question to you. So what do you think? Which placement is more attractive? Okay, so I guess that the answer is obvious. So there's the left picture, there's the left position, the left placement is more attractive. And pay attention that actually it's more attractive, so we will have high click probability regardless of the displayed ads. Another example to you. Say we have a user with a very high past click activity, so very active clicker. And now we just want to compare the click probability of this user to another user, which usually doesn't click. So where you expect to have high probability of click? Again, the first situation provides our how high probability of click regardless of the displayed ads. So how could we quantify this variance? Our answer is with the help of contextual models. So since contextual models are based solely on contextual features, we would like first to categorize these features. And as Jan already mentioned, we have three main three main groups of contextual features. The first group relates to the user features. So we have here location, geolocation, like country, information about device of user, say it was Chrome on mobile, and the historical features. So all the information that we have about the past user activity, past user engagement. So this is the first group of contextual features. The second group of contextual features relates to the web page where we show our recommendations. So it includes the information about the publisher. So was it CNN or the New York Times or the Marker? It includes the information about page category. So was a recommendation showed on news, on sports article, or finance, for example. And it also includes information about page URL. There are other web page related features, but I believe that you get the point here. And the last group of contextual features includes information about placement of a specific recommendation on a page. So it includes the position on a page. So was the recommendation shown on the top of the page or the bottom or probably the side? It includes information about dimension of the ad and information about viewport distance. And now we have 3 examples which show the variability of actual CTR as a function of some chosen features. Where actual CTR is the ratio between the clicks and impressions. And here we normalize the CTR by the global average CTR. So the first plot here shows that the users in Germany are more active clickers than those in Israel. And the users in Singapore, it's slightly above the average. From the second plot, we can see that if an ad was displayed on the entertainment page, we have high click probability compared to the ads that displayed on business and finance articles. And just a theory why it happens, probably users reading business articles are more focused and serious, and those that are reading entertainment articles are more open to other opportunities, in particular to click on ads. And the last plot shows that on mobile devices, we have higher click probability compared to the desktop devices. And here, again, the theory, this happens because it's much more convenient and easy to click on mobile compared to desktops, since we don't need to move our mouse to interact with the ads. Okay, so as you already understand, the primary goal of context-based CTR models is to measure, to quantify supply variance. And now I want to show you that it really works. So to demonstrate this, we take all our supply, all our requests, and divide them into 20 equal size buckets according to the predicted CTR, in such a way that the first bucket will contain the lowest predicted CTR, contextual predicted CTR, and the last bucket will contain the highest contextual PCTR. And then for each one of this bucket, we measure how many clicks fail for each one of these buckets. And the number of clicks we normalize by the global average of clicks. So what do we see here? That the number of clicks grows monotonically with the prediction, with the contextual PCTR. But actually, this is as expected, right? Because this is a prediction of CTR, probably partial prediction, but still a prediction. And so it gives us information that we're in the right direction. But moreover, we can see that most of the clicks come from the last few buckets. And this means that we just identified the highest level of supply which contributes the most of the clicks and therefore has larger revenue potential. Okay, and now given that we have such a nice signal, how can we use it in our system? So essentially we have 2 different applications of a contextual PCTR. So the first application is to optimize computational resources in our system. And the second application is the improvement of our main CTR prediction model. So let's focus on the first application. So it's optimization of resource allocation. So the main idea of this approach is basically comes from this clause that you are already familiar with. So if you remember, we just know how to identify the most potential supply which is more profitable. And the main idea here is just to invest more resources, more computational resources into this more profitable traffic. Okay, so since we have quite a high cost of serving in our systems. So we want to move some of our computational resources from less profitable traffic to more profitable traffic. Okay, and there are many places where we can use this idea in our systems. Just to test a few examples. So you can use more sophisticated models for more profitable traffic. You can rank more ad candidates for more profitable traffic, just to bring more ad diversity and therefore more revenue. So with this approach, we can have both profitability and efficiency. And now we have the second application of our predicted contextual PCTR, which is an improvement of our main CTR model. So the main idea is to use the contextual model as an auxiliary model to our main CTR prediction model. What does it mean? So in this diagram, we can see that the contextual PCTR from the contextual model is used as an additional contextual feature into the main model. And now I just want to raise some very important point here. So as Jan already mentioned, we need to rank many ad candidates during the auction. So it means we need to rank a few thousand of candidates, and it means that we need to compute a PCTR for each one of them. But actually, contextual features are the constant for all of them. Therefore, we need to compute the contextual PCTR only once. So this is a very important point, and we will get to it later. Okay, so if we know that we have a new signal, new features that we want to add into the main CTR prediction model, so we just need to understand what is the way, how exactly can we do this. So we have two different approaches. The first one is called replace, and the meaning of it, we just take all the features that included in the contextual models, remove them from our main model, and instead of them, we just add the new signal, new contextual PCTR feature. And so this is it. So we just reduce the size of the model quite dramatically, and so we just replaced all the contextual features with only one feature, which is a contextual PCTR. This is the first approach. The second approach is called add, and according to this name, it's just adding this new signal on top of the existing features. So by doing so, we actually introduce some information redundancy into our model, but we will see in a moment that actually this information is not redundant at all. Okay, so here I just to share with you the results of our offline experiments where we run these two different approaches, replace and add. So to measure performance of our experiments, we use two metrics. The first one is relative information gain, or RIG. So the exact formula of this, it's written here, but actually you can think about RIG as a normalized log loss for those who is more familiar with log loss metrics. And the main goal of this metric is to measure the quality of the prediction. And the second metric is the computational complexity measured in terms of floating point operations, flows. And the reason why actually we started to look at this metric, because we know that with our approach, we can reduce the size of the model, and therefore we need to understand what is the impact of these changes on the computation complexity. So in the table, you can see the comparison of these two approaches. So where the first line corresponds to the replace approach, and the second line corresponds to the adding approach. So for the replace approach, we can see quite a nice RIG lift, but a very dramatic improvement in a computation complexity metric. And I just want to emphasize that this improvement is very impressive. In particular, if you remember, Jan mentioned that we have over 1 billion of prediction in a second. So imagine how much savings do we have here. And for the second approach, for adding approach, we have a more significant improvement in terms of rig metrics and some drop in the flops. So essentially, it gives us some trade-off between these two metrics, and we can just choose a suitable point on this trade-off and optimize it. So we decided to proceed with the add approach. So we just add one new feature, a contextual prediction on the top of the existing features. And so we trained this model by using a few months of Outbrain's log data. And then we tested this model in our A/B testing system. It means that we serve a portion of a real production traffic in Outbrain. So what can we see here? By the way, we measure the performance of this A/B test in terms of revenue per 1,000 impressions. And you can see here a consistent lift of about 1% of revenue per 1,000 impressions. And this is quite impressive, in particular, when we translate these numbers into the annual revenue. Okay, so we have reached some point where we have discussion points and considerations, and Jan will take us through this.
Thank you, Natalia. I'm taking over the last category, and before we wrap up, I thought we could maybe look at a few considerations we could have when implementing this in production. So first, we talked about like how much the serving costs, and now we said we have an additional model in serving. Like where are the extra compute costs, where's the latency? But as Natalia mentioned, luckily the new model is pretty small. It only does one extra computation per request, so it does not add a lot of costs. And if we go even further, we also show that using this prediction in our main model can decrease that model size quite a lot. And that's also quite nice as it can bring us savings. Another point connected to this one, why didn't we just expand the main CTR model and like do this with a sub-network, like a part of the neural network that we use? Again, the main reason is compute. Usually two large neural networks are quite compute intensive. They like cost a lot to evaluate. So under our latency constraints, this would probably be hard to implement. However, this is an approach that we are quite willing to try in the future. Maybe another point to make here is that if you put these two models into one, this is another trade-off, right? Now you have one model, which kind of takes care of two things, and you need to adjust probably your training pipeline for this. While in the setting that we have now, both models are kind of separate, independent, and you can probably reuse a lot of the functionality that you already have. So the last and probably most important point is that now we have a dependency between models. So for example, now we need to consider, like, what if we want to improve our existing model, like the main CTR one? Do we keep using the same context model, or do we introduce a separate one for the test? Like, how do we even define this test, right? Again, like A/B testing here is quite important, and you need to know how to do it correctly if you want to do improvements correctly. Okay, so let's now maybe wrap up. As we said, the contextual model that we introduced is mostly a simple way to quantify supply variance. We use it for two main use cases. One is optimization of our resource allocation, so to direct more compute to more profitable placements. And the other one is enhancing our CTR prediction models. There are also additional applications that we didn't mention so far. One of them is exploration. We actually published a paper about this at RecSys last year. And another very, very similar application is contextual conversion rate prediction. So basically doing the same thing, but for conversions instead of clicks. There are also other domains this could be applied in. So if you're using an online recommender system, maybe a good question to ask is if this approach is applicable for you. If you're interested in our paper, the Zoom is overlying it, maybe I can hide it. Okay. Here's a QR code, scan it and it'll take you to archive, but as the Moshe already said, you have everything on the website. And if you're interested in talking to us a little bit more, here are emails. Thanks for listening. Thanks to the organizers for inviting us, and I believe we have some time for questions.
You can repeat the questions for you.
Yeah, thank you for the great talk. I learned a lot. So 2 questions. The first one is, do you need to retrain the context-free CTR model often? And the second question is, when collecting the training data for the CTR context-only CTR model, do you randomize the items to expose less popular items, or would the training data get affected by the main CTR model?
Okay, so the first question is how often do we retrain the context CTR model? The question is that we train it exactly in the same manner as the ordinary one, so every few minutes. The second question was, do we change the training data for the contextual CTR model? Like, do we randomize the items and like other things? The answer here is no, that we do not, simply because this, unless we like compute this in production, we don't have the actual effect of choosing another ad, right, to submit. So we cannot do this correctly.
So just a small addition that actually the goal of contextual models is to capture all the information included in the context. It's just doesn't depend on the item itself completely, just separately.
Adding to that, but if I show very, very bad ads to a very good sites, I think the overall average of that context, the CTR should drop as well, right?
So the question was, if we show very bad ads on a very good supply, should it impact, the final supply at the end? Okay, so this is the role of our main CTR prediction models, that just to match, good ads with a good supply. Okay, so this is actually this what we expect, from combination of the item side and the context side at the end. Do you want to add something?
Hi. Thank you. Very interesting talk. I also have 2 questions. So first of all is, I think in the slides there is one talking about the clicks versus contextual CTR bucket types relationship. So I have a question. So by using the contextual CTR to boost and demoting traffic, is it going to cause a significant selection bias? So my question is, if you look at the graph on the left end, all the buckets having 0 clicks for each of them, is it because some kind of pre-selection bias enforced by the contextual CTR that is causing this phenomenon? And what kind of, for instance, exploration mechanism did you exploit to handle this kind of selection bias, potential selection?
Okay, so I can try to formulate your question a little bit shorter, but sure. So the question was, do we have some selection bias specifically on the low contextual CTR buckets, as we can see here in the plot? So is it correct summary of your question?
I think that's a good summarization. Yeah.
Okay, thank you. Okay, yes, we do have some selection bias here. I believe that in general, this contextual signal provides us some kind of selection bias at the end. but actually it does it not in a straightforward way. It predicts, it gives some more deeper interactions from the context, and therefore it indeed provides some information about this context and the bias. Is it answers your question or not really?
Did you do anything special to kind of help with adjust this kind of selection bias in your framework?
I mean, it just captures the information, what is the quality of this specific location. So therefore, once we know this is information included in the main prediction model, right? So this kind of, by the definition, selection bias, right?
Okay. I guess my second question is, later you mentioned one thing you have tried out is you use the prediction from the contextual CTR directly as a feature to the downstream CTR model. I guess my question is, the features used to generate the contextual CTR seems to be a very standard feature that we are also going to use for the CTR model. So why can't the CTR model directly take up those information and patterns from those features? Why does it need to take some kind of two-stage setup to learn from the prediction from a previous model? Because usually when we go with those two-stage setup, not end-to-end setup, we introduce additional noise during the two stages, right? So I'm wondering if you can share some intuition behind the same.
Yeah, so just shortly formulate your question. So the question is why actually does it work, right?
Or why it improve our policy?
Okay, so just the question, why actually we need to include the same signal twice? So we have the same contextual features included in the main CTR model, and in addition included as a specific output of the contextual model, right?
Yeah.
So we don't have a clear answer on this, and our theory is that actually with this approach, we capture some more deeper interactions between the features. And so probably, as Jan mentioned, probably, just by using much more, deep model with a higher, with a larger network, we could capture it as well. But we do have some restrictions in our computation resources. Therefore, this is a very simple approach and it works.
I see. I guess one quick follow-up is you use the contextual CTR for your upstream retrieval, right? Because you mentioned you use it to focus your investment on certain candidates. So I'm wondering, maybe one reason and the same is this signal is used in upstream retrieval to pass it down to the downstream ranking model. It helps the downstream ranking model to get more aligned with the upstream retrieval task.
Jan, could you?
Sure. So the question was like, why do we use it in two places, right? Both downstream and upstream, if I understand correctly?
Yeah, I guess one of my questions is whether by introducing this signal into the downstream, you are enforcing some iter retrieval and the ranking stage alignment between your models. Because in previous slides, you mentioned the context PCTR is used to boost certain candidates that you are predicting or retrieving in one slide.
Oh, yeah, maybe a slight misunderstanding on that part. I think so your question was like, do we use to boost it in upstream as well as then use it in downstream, right? So the upstream part is just choosing how many candidates, it doesn't have a direct effect. So it's just implicit, how many are you scoring? That's the resource allocation part. Got it.
Yeah, thank you so much.
Thanks for the excellent talk. I wanted to ask one thing. Do you also use the prediction from the context here to choose the complexity of the model in downstream? So as she mentioned, right, so some bias will actually be not very relevant in terms of revenue. So we can actually use less complex model in that case.
So the question was, do we use the context CTR prediction then to kind of choose how complex of a model do we want to evaluate for the downstream task, right? That's a great question and a great idea because the answer is no. but I'll consider it.
Yeah, actually, so this one of the ideas how can we use this feature that I mentioned that in our presentation, and this is exactly the way how we can save some of our computational resources, right? So probably for some low profitable supply, we just don't need to apply too much, too sophisticated model. Yeah.
Thank you.
I can ask like 2 questions if there is no other questions. I believe like what you did here is basically a contextual modeling approach where you take like the context and incorporate that as a feature or instead of the features inside your main model. Did you try to maybe use the main model, but either pre-filter or post-filter the candidates or the advertisements based on the context? So based on the CTR context that you calculated, you can re-rank and then evaluate the main kind of list of rankings. So before or after, and then see how it influences. And maybe that will also answer one of the questions that raised, why do we need another model to produce another metric for your main model? And my second one is...
Let's take it one by one. Okay, so the question was, if I understand correctly, was the approach of contextual models, is it possible to use it to change the ranking process, actually? And the answer is no. And this is because during the ranking, we have the constant context, right? So during the request, all the candidates have the same context. Therefore, we cannot play with it. This is given. And so we cannot impact the ranking in this place. But what we can do here, just, to rank more candidates, based on this idea of more bringing more resources for more profitable traffic. Just for example, if we have usually X thousand ads ranked during the ranking process, and now we believe that this specific context will give us for sure some high revenue. Therefore, probably we need to bring more candidates, and then to ensure more ad diversity here, and and to bring more revenue.
Thank you. And my second one was, did you try to rank which type of the groups that you mentioned, the user one, the ad one, and so on, which type of contextual features really influence the main kind of feature?
Yeah, so the question was, did we try to rank the groups of features to see what impacts? So we didn't show this real directly, but in our AutoML process, which kind of selects models, like builds good models, we did do this like just indirectly, right? The AutoML process builds feature by feature and then gives you this information. So yeah, usually like you did see similar features that you intuitively thought are good in the final model build. We can't really disclose all of that, I'm sorry, but yeah, it does function how you think.
Thank you. Any last question?
Thank you for this comprehensive talk. I have one question about the context features. So I assume that if we are working with ads and the context, we are assuming that they are like independent variables. So that the context is independent from the ad that is presented there. But I also assume that you probably have some business constraints where some of the web vendors want to have specific type of ads on their websites. So my question is whether it somehow affects your context, or did you have any problems with that in your process?
So yeah, so the question was like, does the context affect the ads that we choose, right? In a nutshell. So you also said that maybe the publishers are picky about what ads they want to see. I would actually reframe this as the other way around. Usually the advertisers are picky about where do they want their ads to be shown. Like in the like app where they upload the ads, they can select a bunch of filters. Like, you know, I want users from Singapore who are, I don't know, interested in Formula One, and then this filters our ads quite a lot before we can actually, you know, pick them, because we filter them on a given request. So I would like look at it more from this perspective.
Okay, but you didn't have to somehow normalize or align these context features in any way.
Not for the purpose of your question.
Okay, thanks.
So let's thank the speakers again. All right, so Konstantin will be responsible for the next session of papers. He will be joining us online. Thank you, Konstantin, for joining us remotely. We will hear from the screen. Due to time differences and other kind of challenges. So again, thanks for participating here with us. Yeah.
Can you hear me? Hey, Moshe, can you hear me?
Yeah, we can hear you.
Okay. All right. Hello, everyone. My name is Konstantin Baumann, and I would like to thank Moshe for being on time. So right now we are switching to a paper session. We will have 3 presentations. Each presentation is 15 minutes. 12 minutes for presentation, 3 minutes for question. And our first presentation is called Multitask Learning for Reduced Popularity Bias in Multi-Territory Video Recommendations, presented by Zhen Wen. So please.
Yeah, thank you for the introduction. It's me again. I'm presenting another paper from the team. So if you listen to my previous presentation, probably know the background of our application is for promoting Amazon-owned titles in our front page. So this one is talk about the challenges when we try to expand the system to different countries and then different specifically for different countries. So of course, if you are talking about the challenges to expand the recommender system to worldwide, then there are 2 naive approach, of course. One is to create a recommender system for each of the country using their data to train the system, but it's a huge burden for operation like Amazon Prime Video is more than 200 countries. So running 200 different models for each different countries will be a great, huge operation challenge. And also some countries, the number of audience is small, so the model may not be stable. And another simple approach, of course, is to use one unified model for all the countries. And then for this approach is that different countries have different characteristic, the different cultures, they like different content, so that if we use one single model, so then the global titles, meaning that titles are popular in large countries like US may dominate in the model, so that if you are a small country like Ireland, you have a good local title, then it may not have chances to reach to the audience. So that's the popularity bias that we need to deal with in this global expansion of the recommender system. Yeah, so it's summarized here. There's the popularity bias and the unfairness for local titles. So the solution we propose to address this challenge is the multitask learning, which is also used a lot in large language model as well. So here in this context, multitask learning is trying to capitalize or utilize the commonality between different countries, like use a strong country with a lot of viewers to help those smaller countries. And also, meanwhile, in this multitask learning settings, we also try to learn the different characteristics of different countries as well. And yeah, so we believe it as our first application of the multitask learning to mitigate the popularity bias in a global setting, a global expansion setting. So a few techniques we use in our multitask learning is one is the data upsampling strategies. So here we use different groups of users, like each group represent a market, like a country, for example, so that we can ensure for each of the group we have a representative sampling data samples that we can learn the model. And then we use the MTL approach to learn the representation at the territory group level and shows that our proposed model can reduce the popularity bias. So of course, our first technique is to do upsampling. So here we don't sample the data according to how much streams we have, then it will be subject to the popularity bias. So here we try to select the disjoint set of active users so that we can have representative representation for each of the market that we're trying to expand to. And so it will help the smaller countries like Ireland so that their local titles can stand out in the promotion ranking as well. So here is one of the model that we used in the recommender system. So here is the title user propensity model. It's a two-tower model. So input to the two-tower, one is the title embedding, the other is the user embedding. And for the user tower, we created n groups. So each group is corresponding to a representative grouping of the user in the particular country. And then we treat each group as a task. So the training data, we use the order of 10 million random sampled from the disjoint set of the users. And then we have like hundreds of titles we trained, we promoted for the last several months. So for the inference, we again used the same amount of several millions of data, and then evaluated our model on the 3 different disjoint tested data for 3 consecutive days. So here is the result. We compare the PR AUC gain for the user title propensity scores. So here each T here is the different countries. So we listed here 16 countries, and we see the MTL approach, 3 different treatment, and then we see overall improvement of the MTL approach. And also you can also see that the MTL approach, the improvement for different countries are still different. So for a country that follow the global trend, then the improvement is smaller. But for a country have a unique characteristic, then the MTL approach will have larger improvement. And this is a case study on the title level. So remember that we want to give the individual titles a good chance to reach to their potential customers. So we look at the two different local titles and the two global titles. We compare to the MTL approach versus baseline, and also versus the baseline with the upsampled technique. And here is the relative improvement of the PR AUC. So again, we see the good improvement for all the 4 titles, but for different titles, again, they have different improvement. So for the last, for the global title 2, we see much bigger improvement. And the reason we think is that this has a different feedback from different countries, depending on the culture, so that if we use a uniform, like a baseline approach, doesn't use MTL, then the performance will get hurt by the global unified treatment. But using the MTL, it helps the individual characteristic of different countries can be represented better. So another case study, we look at the score distribution, basically the user title propensity score distribution, to see how it can help the local titles. The 3 different colors, blue is the MTL approach we propose, green is the baseline, and orange is the baseline with upsampling. So we see that for the local titles, we push the distribution, score distribution to the higher side, to the right side, meaning that we found more users have a higher probability of start to stream these local titles, which will help the co-start of these local titles. And for another case study is the global titles. So in this case, we want to see whether we can move the score distribution to the lower side, meaning that we have a fewer popularity bias for this title. Will measure the success based on the local feedback from the local market, rather than using the global success to just to push it out all over around the world. So here we see that indeed the global titles distribution moved to the lower side with MTL. Okay, so let's conclude. So because we want to push a recommended system to global market, and then we try to come up with a practical yet effective approach, right? Using a unified approach, but with the MTL approach that can utilize the similarities of the different countries, but also same time to learn the unique characteristic of the different countries. And we use disjoint active user groupings to select the representative group users for each of the market that we try to expand to, so that we ensure they have the better customer experience. And and the proposed method have more than 65, up to 65% of the relative PR AUC. And yeah, I know there is a question from the previous presentation. So we are in the process of doing the online A/B testing for this approach. So we don't have result yet, but it's a work in progress. Hopefully towards the end of the year, we'll have the results to report. And the other future work of this MTL approach is also on how we can expand the video recommendation from one offer type, like one business type, to multiple business type. So here is one business type is a subscription-based video streaming, meaning that once you join, for example, Netflix or Amazon Prime, you have this right entitlement to stream the video. So that's a subscription-based video streaming. And also there is a transaction-based video streaming, meaning that you can buy or rent a particular movie. And then there's like ads-based video streaming. For example, you see ads so that you can stream certain titles free. So this different offer type also have different characteristics. For example, if it's ads-based, then less people may want to see the ads, and transaction-based, then there is a price war for people to engage with those titles. So we are also expanding this approach to those different business type as well. Yeah, so I think that's all for my presentation.
All right, thank you, Zhen. Do we have any questions from the audience? Okay, so, oh, sorry.
Yeah,
Let's go ahead.
This is actually some practical problem we face as well. So I guess one question is back to the model architecture. When you are talking about you set up multitask learning for different countries, does it mean you have, for instance, one task for US CTR prediction, another task is Indian CTR prediction, and so on? So can you explain a little bit more on this part?
Yeah, so here the task is, the question is, for this multitask architecture, whether it's for each country, like US, we have a task for CTR prediction, and then India CTR prediction. And the answer is yes. But here the task is not predicting CTR yet. This is predicting the title user propensity. So it's an intermediate result for our recommender system. And each of the group is one group in the country, so that we are learning for each the different tasks here. Yeah.
Yeah. But a follow-up question is, by upsampling the underrepresentative countries, you are essentially downsampling the dominating countries. I'm wondering, during this approach, have you observed a performance drop for the large traffic countries?
The question is that the upsampling approach essentially is downsampling the popular big countries. Will that be a drop in the performance? So we, yes, so this is essentially the same as downsampling the popular countries. So we tested several hyperparameters, like how much we upsample, so that we can ensure that the large countries are not affected. Yeah.
Yeah, just a quick follow-up. So you mentioned you tested several ways of sampling. I'm wondering in the end, how much do you sample? I suppose it's not to upsample every country to have exactly the equal kind of traffic in your data set, right? I'm wondering, can you give us some kind of example to which extent you upsample those smaller countries?
So this is the detail. I need to get back to you. So if you want to, I can follow up with me on details.
Follow up.
Yeah.
Yeah.
Thank you so much. So as far as I remember, it's
all right. So
okay. Yeah.
In the interest of time, let's take all other questions offline. Let's thank the speaker.
Yeah. Thank you very much.
Thank you. And let's switch to the next one. And our next presentation is Context-Aware Feature Attribution through Argumentation by Jennifer Zhong and Elsa Negre.
So can you hear me, everybody?
Yes.
I can hear you.
Yes.
Yeah, Moshe, thank you.
Okay, and now I will share my screen. The whole screen is here. Just to make sure that everything, okay, wait a minute. I will make it full screen. So can you see my screen right now?
Yes.
Okay, so maybe I can start or, okay. So I will start my presentation. So good morning, good afternoon, and maybe good evening, everyone. I'm Jinfeng Zhong from Paris Dauphine University, and Elsa Negre is my PhD supervisor. Our work is about context-aware feature attribution through argumentation. So today I will start by introducing the core ideas and motivations of our work. So let's start with some intuitive assumptions of this paper. So the first is that features of an item can influence users' preference towards items. And this influence can be positive, negative, or neutral. And with this, we can see that the features can naturally be regarded as arguments that influence another argument, RCI, which indicates that the item can be recommended to the target user. And third assumption is that the importance of feature types vary across users. And fourth is that context can influence preferences. This means that the strength of arguments vary across different contexts. And last is that the importance of contextual factors also vary across users. And before continuing, I would like to clarify some of the terms used in this presentation. The first is about feature type. So feature type, basically, it is a high-level concept. It indicates the exact aspects of item features. For example, the feature types of a movie may include genres of the movie and actors of the movie or directors of the movie. And as for feature, we mean it's the value for feature type. For example, the genres of a movie can be action. Which means that this movie is an action movie. And the second is about the definition of context. Today we have many people talking about the context. There are many different definitions, and we have chosen the definition that suits us best. So basically, context is any information that can be used to characterize the situation of an entity. And this entity could be a person, place, or object that is considered relevant to the interaction between the user and the application, including the user and the application themselves. And in this presentation, we will distinguish the following three terms. The first is contextual factors. For example, to characterize the situation of a user, we can use time, location, and companion of the user. And the second is about contextual condition. It's basically the value of contextual factors. For example, the time, a contextual factor of a user can be weekday or weekend. The location of user can be at home or at office. And companion of a user can be with friends, with family, or with colleagues. And last, contextual situation is basically the situation of a user. So the situation of a user can be someday at home and with family. So now I will introduce, since our work is also leverages argumentation frameworks. So why we use argumentation frameworks? So the first is that by leveraging argumentation frameworks, the decision process can be represented in a graphical way. For example, here we have a decision. The decision means an item can be recommended to recommend an item to the target user. And all these arguments, argument 1, argument 2, argument 3, they are basically the features of items. So we regard features of items as arguments. And second is that we can also represent the strength of these arguments, which can be also quantified by the strength of the arguments. And therefore, the strength, and third is that the strength function of these arguments can be carefully designed to satisfy weak balance and weak monotonicity on all these desired properties. For these two desired properties, maybe we can talk later. I will go on. And here comes to the main steps of our model. So the main idea of our model is to leverage argumentation and user's context at the same time. So the first step would be to get a specific representation for this user, the contextual situation. And the idea is quite simple. We simply multiply the embedding of contextual condition by the importance of the contextual factors, and then add it together with the embedding of the user to get a specific representation of the user under this contextual situation. So this is the first step. And the second step would be to calculate the importance of feature type for this user under the contextual situation. So this is quite simple. We simply adopt the dot product of the user representation under this contextual situation with the embedding of the feature type to get the feature type importance for this user under this contextual situation. And then the next step would be to compute user's rating towards features. This step is also quite simple by adopting the inner product of the embedding of user presentation under this contextual situation and the feature. To get users rating towards feature. And the last step would be to aggregate users rating towards features to compute users rating towards items. So this is done by multiplying users rating towards features by the importance of feature type that we calculated in the second step. And now I will introduce some intuitive explanation applications of our model. So to make it more clear, I will explain the application under a book recommendation scenario. So here is a typical book recommendation. And by leveraging the argumentation framework, we can map the decision-making process or the recommending process into this argumentation framework. So we can see clearly that, for example, we can see that draw 1, it indicates science fiction. It is an argument that supports the recommendation of this book. And therefore, draw 1 is an argument that supports the recommendation of the book, whose strength is positive 0.77. And draw 2, let's see here. It is an argument that attacks the recommendation of the book because its strength of this argument is minus 0.11. Author 1, again, it is argument that supports the recommendation of the book. This also means that this user likes the books written by Will Smith. And lastly, author 2 is an argument. We can see that the strength is 0. And therefore, it is an argument that does not influence the recommendation of the book. So the first intuitive application would be to generate the toy example explanation templates. The SR indicates strong recommendation. So we select the 2 strongest supporters of the recommendation. And in weak recommendation, WR, weak recommendation, we select the strongest supporter and the strongest attackers. And for NR, which means not recommended, we can select the 2 strongest attackers of the recommendation. And we also did some empirical evaluations on 2 datasets. The first on YAP datasets and FKB datasets. So, and we compared with some context-free and context-aware models, and also an existing argumentation-based model, which is called aspect item model, which is also recently proposed. And the results, we evaluated all the models in terms of the prediction accuracy. And we can see that our model outperforms all the context-free and context-aware baselines. While at the same time, our model context-aware feature attribution provides semantics for each step because we regard each feature as arguments, and users reading towards features are regarded as strength of these arguments. And second observation is that compared with existing argumentation-based model, which is called aspect item model, our model can largely improve the prediction accuracy. And third is that by observing from the horizon, by comparing the YAP dataset and the FKB dataset, we can see that our model performs better on FKB dataset. Our interpretation for the moment is that this may relate to the sparsity of the dataset. The sparsity of the YAP dataset is 99.98%, while for the FKB it's not that sparse. And for the ablation study, we did we carry out the ablation study to find how each part of a model may influence the results of the prediction. For example, the FATA, which means feature attribution through augmentation. It means that we do not consider users' context. And a version with average means that the importance of each feature type is the same for users. And our observation can see here that users' preferences towards attributes are different. And also, since CA FATA outperforms FATA and average FATA outperforms average FATA, we can see that context do influence users' preferences. And to make it more, to visualize the results of our model, we represent each user by vectors of 7 of each by vectors that contains the importance of each contextual factor. For example, we did a case study on the FKB dataset. Each user is represented by a vector of 7 seven dimension, because in the Fragkoul data set, there are 7 contextual factors. And then we use k-means to cluster the users. So here is the results of the, and then we use the UMap to visualize the results. And here is the results of the clustering. We can see that users from each cluster, from different clusters, accord different importance to each contextual factors. So here is the average importance of each contextual factors in each cluster. And here comes the conclusion and perspectives. So in this paper, we combine factorization-based methods and argumentation frameworks, because as you may see just now, for computing the feature type importance and for computing users rating towards features, we use simply a DAUT production, which is quite similar in the matrix factorization. And the core idea is that features are regarded as arguments and ratings are regarded as strength of these arguments. And therefore, each step is endowed with explicit semantics. And our empirical study also shows that our model can achieve competitive performances compared with some strong baselines, and also largely improves performance compared with existing argumentation-based model. And our model can generate at least 3 applications. The first is just introduced just now, generating toy example templates. And third application is work after the paper has been submitted. We can generate interactive explanations and also contrastive explanations. I will give you some examples about interactive explanations and contrastive explanations later. And perspectives. In this work, we concentrate on rating prediction. It will be also interesting to extend our work to ranking prediction. And second is to conduct user studies to evaluate and compare the qualities of explanations generated by other explanation methods. So the interactive explanations and contrastive explanations are some follow-up work of the paper submitted to the CARS workshop. Maybe you can discuss later if you are interested. So just to give you an intuitive example of contrastive explanation, by using our model, we can generate such kind of explanation to explain the results of recommendation. We recommend you movie A over movie B due to your preference for action movies. And while movie A fits this role, movie B is a drama. So we can see there that this explanation compares movie A and movie B in terms of the feature of the 2 movies, which makes which will be maybe more intuitive for users to understand how the system have learned the preferences of the user. And here are some references of this presentation. And thanks for your attention.
All right, thank you, Jinfeng. Do you have any questions in the audience?
I don't see any question, and that was
okay.
It's kind of the easiest option because like it will be hard for the audience to come here to the stage. So
wait a second. Yeah. While the next presenter is preparing, I have a question. Like you have evaluated your model based on the accuracy, but at the same time you are studying the interpretability, like how to explain to the user your recommendations. Have you tried any interpretability measures?
Well, yeah, there's upcoming work because it is true that evaluating the qualities of explanation is quite important subject of my thesis, and it is a follow-up work after. We intend to conduct user studies to evaluate and compare explanations generated by our model and other methods. Yes, yeah.
All right, thank you. Let's thank the speaker again.
And thank you.
And
I
go to the next one.
Another metric that is important also is the ranking metrics instead of only prediction, like RMSEs and MAs.
Yeah, there's a follow-up. Yeah, thank you. Yeah, that's an important point. Thank you.
All right. Thank you. So we're going to the next presentation, and we're exactly right on time. The next presentation is called TranSQLation, Transformer-Based SQL Recommendation. I suppose it's presented by Shirin and Tahmasebionatarki. Sorry for mispronouncing your last name.
Hello everyone, my name is Shirin Tahmasbi, and today I'm going to present our recent work, which is named TranSQLation. It's a joint work with Amir Peybera, Ahmed Soilo, Dimitri Roman, and Mihail Matskin. And the outcome of the presentation would be as follows. First, I will have a brief introduction and the problem definition part. Then I will present our solution, which is named TranSQLation. And after that, I will talk about the experiments and finally the conclusion. Nowadays, we are facing with some data that the size of them are growing exponentially. So the point is that if we want to be able to manage such huge amount of data, we need to have some powerful tools. One of these tools can be database management systems. And based on a recent survey, which is conducted by Stack Overflow, it seems that top 5 frequently used database management systems are relational. This means that users need to have some expertise in writing SQL scripts in order to be able to work with these database management systems. But writing SQL scripts can be a bit challenging for users because they need to have some diverse skill set. For example, they need to be expert in SQL syntax, they need to be familiar with the database schema, and they need to have a deep understanding of the application domain. So because users are usually deficient in at least one of these skill sets, so it can be a bit challenging for them to write SQL scripts. The question is how we can mitigate this skill gap, how we can help users to write SQL queries in a more easier way and without getting involved into too much details. So one of the potential solutions for this problem, which is also the objective of this paper, is to have a recommendation system. This recommendation system can help users to write their subsequent or their next query. And the recommendations should be based on the user's previous queries. So before defining the problem, I first need to talk about some concepts and terminology. The first concept is query fragment. By query fragment, I mean all of the attributes and all of the table names which are used in a query. For example, if we have a query like Q, then the fragments can be written as a set of all of the attribute and table names, such as attribute 1, table 1, and attribute 2. And the second concept is query template. Query template itself is a query in which all of the fragments are masked. For example, if we have a query like Q, then the template can be written as follows. And the last concept is user session. By user session, we mean all of a sequence of user queries in chronological order. So if we use QI to represent a user query, then the user session can be written as follows. So with this concept, we can define the problem of recommendation system for SQL queries. And to have a better understanding of the problem definition, we have divided the problem into 2 parts. The first part is the template recommender, and the second part is fragment recommender. The input of both of these modules or both of these parts is the user current session, and the output of the template recommender is the template of the next query, and the output of the fragment recommender is the fragments of the next query. In our work, we are going to focus on the fragment recommendation part, so this is what our solution is going to address. To have a better understanding of what a fragment recommender does, we can have an example. For example, if we have a user session with 4 queries, then let's say that the user session is on the left side of the slide, and then let's say that the next actual query is written on the right side. Then for writing this actual query, we can have some recommendations to the user. Because here we are focusing on the fragment recommendations, so the recommendations can be table names and attribute names. So before talking about the solution, because we have used the concept of language models as a core part of the solution, I need to provide some background. The recent language models are usually pre-trained on massive and general purpose data, and then they are fine-tuned on some smaller data sets to be suitable for downstream tasks. So the input of these language models is textual and tokenized data. And also for using them for different downstream tasks, we can use some special tokens. For example, we can use separation token for separating the sentences, or we can use some classification tokens to make them suitable for classification tasks. Now here about the solution, which is named TranSQLation. First, I use an example to clarify that what TranSQLation does exactly. Let's say that we have a user session with 2 queries. Then because we want to use a language model as the core of the system, so we need to format the input to make it suitable for the language model. The first step is to concatenate these 2 queries to each other and add a separation token to mark end of each query. And then for each fragment in the query, in the whole input, we need to add a classification token exactly before the fragments. So it means that if, for example, here we have 5 fragments in the input, then we have 5 classification tokens. Each of these classification tokens is related to one of these fragments. This is the input of the system. So what is the output? The output is a Boolean vector. So each the size of the vector is equal to the number of classification tokens in the input. And for example, if a label is equal to true, it means that the corresponding fragment should appear in the recommendation list. So here, because the first item and the last item of the output vector is true, it means that attribute 1 and table 2 should be appear in the recommendation list. So by using, for example, these 2 fragments, we can have a query like this one. This is the general overview of the input and output of the system. Now about the architecture of our solution is something like that. First, we tokenize and inject some classification tokens to the input, and then we use this input and give it to the language model. We can use any language model. For example, it can be Bart, CodeBert, or any other one. And then we get the representations from the language model. And then we pass the representation of classification tokens to a recommender layer. This recommender layer can be a binary, a simple binary classifier. And then the output of this binary classifier says that if the corresponding fragment should appear in the recommendation list or not. So to evaluate how our TranSQLation system performs on the different data sets, we have conducted some experiments on 2 data sets. These are the 2 frequently used data sets in the literature. One of them is SDSS, which is for astronomical data. In this data set, there are 11,000 user sessions, and each user session has about 86 queries. And the other data set is SQL share, and it has also about 11,000 user sessions, but here each user session has about 12 queries. So SQL share is much smaller than SDSS. We have first done the experiments on SDSS, the larger data set, and we have proposed 2 variants of TranSQLation. In one of them, we have used Bart as a core language model, and in the second one, we have used CodeBert. So the first variant is called TranSQLation Bart, and the second one is called TranSQLation CodeBert. We have reported table accuracy and attribute accuracy as the performance metrics, and we compared our 2 variants with 3 baselines. So as you can see, both of the TranSQLation variants can outperform the baselines in both of these 2 metrics. But the point is that TranSQLation Bart seems to have a better performance. So we took the TranSQLation Bart variant, and this time we have used SQL share datasets to fine-tune this TranSQLation Bart. So as you can see here, the TranSQLation BERT result is in the first row of the table. So we can get a comparable result to the baseline, but we couldn't outperform them. So the reason is that because SQL share data sets, in each session there is much less queries compared to SCSS. So this is the reason. So we have decided to use the transfer learning ability of our model, and we have proposed a second variant, which is named TranSQLation BERT transfer. In this variant, we first fine-tune the model on SCSS, and then we fine-tuned it on SQL share. So as you can see, by using this strategy, our transferred model can achieve a better performance compared to the baselines in terms of both of these performance metrics. So it means that for large data sets, our solution can perform very well. And even for smaller data sets, we can use this transfer learning ability to outperform the baselines. So as conclusion here in this work, we have proposed TranSQLation. It is a transformer-based solution for fragment recommendation, and it is sequence aware, which means that we take the sequence of SQL queries into account. It is session aware, which means that we consider the history of queries in a user session, and it is context aware, which means that we consider the semantic similarity of queries because we have used contextual word embeddings. And also we could achieve 22 performance improve on large data sets. And for future work, we are planning to use large language models such as GPT or Llama. And we are planning not only recommend fragments, but also provide full SQL queries for recommendations. Thanks for your attention. If you have any questions, I would be happy to answer.
Thank you. Do you have any questions?
Thank you. If I understand correctly, you recommend the most relevant token or attribute for the SQL query and compare the ground truth item with the recommended token, if I understand correctly how it works. But I think in practice, your recommended item couldn't be inserted in the SQL query just because the table doesn't have such attribute. And in this case, I think you should check if a recommended attribute can be launched as a query.
The question is that maybe some recommendations are not accurate based on the database schema. Yeah, that's correct. And there is, this is a big point that exists in all of the baselines. So yeah, it should be considered also as maybe in the future work. Thank you.
Do you have any other questions?
Yeah.
Thank you for the talk. I have one question, like, does your TranSQLation model also able to predict some more complex queries? So for example, let's say user did a group by operation or something, and then let's say next, what do we want to do?
So I didn't understand what you mean by complex queries.
So for example, let's say suppose user did a group by operation, and then maybe then you want to, can you, like, based on users past activities, you want to, like, see, okay, group by and then aggregate is the next thing. So is it also in the scope of this?
So the question is if the TranSQLation supports complex queries with complex statements. Actually, we are recommending fragments, which is only table names and attribute names. So we don't care where it can be used. So the answer is that we haven't considered in this work, but for future work, because we are going to recommend the whole SQL query, so we are going to take it into account. Yeah. Thank you.
All right, so let's thank the speaker.
Thank you.
So it's time to conclude our workshop. First of all, I would like to thank Moshe Unger. There are 5 organizers in our group. We were all working on preparing for this workshop, but Moshe was the only person who was able to be there, unfortunately. So Moshe, thank you for handling this. thank you everyone for coming. That was a successful workshop. Lots of people online, lots of people in the room. So I'm sure we will continue that in the next year and hope everyone will come. Moshe, would you like to say a few words?
Yeah, I think it was very successful workshop. The room was packed in several kind of times. First of all, thank you all for coming for the first day of the conference. Most of the people before the conference starts like explore the city. So hopefully you'll have enough time to do that today afternoon. I think in the next year, we're gonna focus, hopefully once we will get accepted to the next year conference, we'll focus on the applications of LLMs in context-aware recommendation, based on also what Marius showed us today, more interpretation of that models of how contextual information can be integrated in those kind of large language models. Also focusing in other kind of aspects of group recommendation as one of the presenters today, and dynamic importance of context. And finally, because in the industry and academia, we don't have enough kind of baselines and data sets, offline data sets to compare to, I believe that also papers with explanations of the data sets and sharing context-aware data sets would totally be important in our field. I also invite you to submit your papers to the next workshop in the next year, and wishing you, all of us, a great conference, and thanks again for coming. Thank you. Have a great day, everyone. Thank you. Thank you, Kostya.
Bye, everyone. Thank you, Moshe.